we are going to start with the working principle of another very popular tool for multi-objective optimization, and this is known as non-dominated sorting genetic algorithm, in short NSGA. Now, the initial idea of this NSGA came from Professor David Goldberg, and the first version was developed by Srinivas and Deb, and later on it is further modified by Agarwal, Deb and others. Now, let us try to see the working principle of this particular the non-dominated sorting genetic algorithm. Now, let us start with step 1. We sort the population into a few ranks, say 1, 2, 3 and so on. Now, as we discussed that a GA starts with a population of solution selected at random, and what we do is the first we try to sort them into a few ranks based on their fitness values. So, we compare the fitness values of two solutions and try to find out which one is the non-dominated one. Now, the rank 1 front consists of all non-dominated solution. So, the whole population can be divided into a few ranks like rank 1, rank 2, rank 3 and so on. Now, I have already discussed how to do this particular the ranking. Now, once you have got this particular rank, now we can proceed with like the first operator, that is reproduction, and the purpose of reproduction is to select the best solution probabilistically just to form the mating pool. Now, supposing that, let me concentrate on this particular problem. Now, here we are going to minimize two objectives, say f 1 and f 2, and supposing that from the initial population selected at random. So, we are able to sort into a few ranks like your rank 1, rank 2, rank 3 and so on. Now, if I compare a particular solution from rank 1 and another solution from rank 2, definitely. So, this particular rank 1 solution is non-dominated with comparison with your the rank 2 solution. That means, this particular solution, the rank 1 solution is slightly better compared to this particular solution in terms of the objective function. Now, if we consider the average fitness of rank 1 solution, average fitness of rank 2 solution and average fitness of rank 3 solution. Now, it indicates that the average fitness of rank 1 solution will be better compared to that of rank 2, and the average fitness of rank 2 solution will be better compared to that of rank 3 solution and so on. Now, if I just go for the reproduction scheme just to get the mating pool, there is a possibility that in the mating pool there will be more number of solutions belonging to rank 1, and so this particular number of solutions belonging to rank 1 is going to increase in the population. That means, there will be some selection pressure, and gradually what will happen is, so the mating pool will consist of the more number of better solution, and consequently GA will try towards determining the optimal or the globally optimal solution. So, in this way actually we can ensure the selection pressure, but as we know that if I want to ensure a very efficient search for the GA, so we will have to maintain a proper balance between the selection pressure and population diversity. Now, I have already discussed little bit how to ensure this particular selection pressure by selecting more number of rank 1 solution in the mating pool. Now, let us see whatever I told here. So, those things I have written it, that the average fitness of rank 1 solution is better than that of rank 2 solution. Similarly, the average fitness of rank 2 solution is better than that of rank 3 solution. And we carry out proportionate selection. Now, here in proportionate selection, which we have already discussed, the probability of selection is proportional to the fitness. So, there is a possibility in the mating pool there will be more number of rank 1 solution, and which is going to ensure the selection pressure in this particular the GA search. Now, let us see how to maintain the diversity. Now, as we have already discussed several times, that to ensure a very efficient search for the GA, a proper balance between selection pressure and population diversity has to be maintained. Selection pressure we have already discussed. Now, I am just going to concentrate how to get or how to ensure the population diversity. Now, let us see how to ensure the population diversity. Now, let me for the time being concentrate on the rank 1 solution. Now, if you see the earlier figure, now you can see that in the rank 1, so there are 13 solutions. Now, out of these 13 solutions, we can see that solutions 1, 2 and say 12 and 13, they are far from the other solution. Now, here there could be a very close solution like 3, 4, 5, 6 and all such things. They are very close, but these two solutions 1 and 2 and these two solutions 12 and 13, they are too far from the other solution. So, I am just going to consider there are 13 solutions on the rank 1, and out of 13, 1 and 2 and then 12 and 13, they are too far from the remaining solution. Now, this is the problem. Now, if this is the problem, then there is a possibility that in the next iteration or to the next iteration, the end solution like 1, 2, 12 and 13 will be deleted from the population, and there is a possibility we may not get the whole the stretch of this particular the Pareto optimal front of solution. That means, a part of the Pareto optimal front could be lost, and if it is lost, then the diversity from the GA search, so that will be lost, and that is not a very efficient search. Now, how to ensure ensure that all the solutions should be there in this particular Pareto optimal front, and the stretch of the Pareto optimal front will be maintained. Now, to see this particular thing, how to maintain this particular diversity, so we take the help of this step 3. Now, here actually what we do, so we have considered 13 solutions in the rank 1, and as I told, solutions 1, 2, 12 and 13 are too far from the other solution, and there is a possibility those solutions will be lost. That means, a significant part will the Pareto optimal front will be lost from the GA solution. Now, to overcome this particular problem, we use the concept of sharing. Now, let us see how to use this particular the sharing. Now, to implement the concept of this particular sharing function, we take the help of the Euclidean distance. So, we try to calculate the Euclidean distance between the 2 points I and j, that is denoted by d I j, and once we know this particular Euclidean distance using this particular expression. So, we can find out what should be the sharing between the 2 points I and j, that is denoted by s h d I j. So, the sharing between 2 points d I j is nothing but s h d I j, and that is nothing but 1 minus d I j divided by sigma share square if d I j is less than sigma share. Otherwise, so this particular sharing between the 2 points I and j will be assumed to be equal to 0. Now, here this particular sigma share is a fixed numerical value, and that is actually assigned by the user. How to assign this particular sigma share value? It depends on the experience of the user, and of course, it depends on the problem information. Now, this I am going to discuss after some time in more detail, but for the time being let me see, if I know the distance between the 2 points I and j. So, how to determine so this particular the sharing function value. Now, here I just want to mention, if the distance is less than sigma share, the predefined fixed value, then only, so I will be getting some non-zero value for this particular the sharing. But if the distance is greater than equals to sigma share, that means the 2 points are too far, then the sharing between them will be equal to 0. Now, using this particular principle, and if I take the same example, now I can come to the conclusion that the points 1, 2, 12 and 13, the sharing value, the sharing function value will be very small. On the other hand, for the remaining points like your 3, 4, 5, 6 and all such things, all such points up to 11, the sharing function value will be somewhat on higher side. Now, what we do is we try to calculate the niche count. Now, the niche count is nothing but the summation of the sharing function values. Now, if I assume that there are 13 points on the rank 1. So, what we do is for each of the 13 points we try to find out what is the niche count value, and if I just find out the niche count value, we will be getting the information that the niche count for the points 1, 2, 12 and 13, which are too far from the other points, the niche count will be less, and the points which are lying very close to each other, that is 3, 4, 5, 6 up to say 11, the niche count value will be somewhat higher. So, the same thing I have written it here for the points 3, 4, 10 up to 11, the niche count will have some higher values. Now, what we do is we try to calculate the shared fitness. Now, the shared fitness is nothing but the individual fitness divided by the niche count, and we have already discussed the niche count value for the points 1, 2, 12 and 13 will be less. That means, the shared fitness for the points 1, 2, 12 and 13 will be more compared to that of the points 3, 4, 10 and 11. Now, let me summarize whatever I discussed. So, what I do is, supposing that there are 13 points on the rank 1 front. So, for each point I try to find out, so what will be the niche count. Now, niche count is nothing but the summation of the sharing function values, and to determine the sharing function values we take the help of the Euclidean distance. Now, if the points are too far, then the Euclidean distance will be more, that means the sharing function will be less, and if it exceeds, if the distance between the 2 points exceeds a certain predefined value, the sharing between these 2 points will be 0. That means, the points which are lying on the ends, the 2 ends which are too much distant from the other points, the sharing function value will be less, and consequently, the niche count will be less. And that is why, for the points 1, 2, 12 and 13, the niche count value will be less, and the shared function, shared fitness is defined as individual fitness divided by niche count. Now, what we do is, the individual fitness initially we assume that they are equal, and the niche count value for the point 1 to 12 and 13 will be more, will be less, the niche count value will be less compared to the other points like 3, 4, 10 and 11. Consequently, the shared fitness of the points 1 to 12 and 13 will be more compared to that of the points 3, 4, 10 up to 11. Now, if I do the reproduction or the proportionate selection based on the shared fitness in place of the original fitness, so there is a possibility that in the mating pool there will be more copies of these particular points like 1, 2, 12 and 13. Now, if I get more copies of the points 1 to 12 and 13 in the mating pool, so this mating pool is going to participate in crossover, and after that there will be mutation, and there is a possibility that in the mating pool as we have considered good solution. So, in the we will be getting slightly better children solution, and by doing that the population diversity will be maintained for this particular the GA population. Now, this is the way actually we can incorporate and we can maintain the population diversity in the GA. So, this is how to maintain that particular the population diversity in the GA. Now, whatever I discuss, the same thing I have written it here. If proportionate selection is carried out based on the shared fitness, there is a chance of getting more copies of 1 to 12 and 13, these points will not be lost from the Pareto front and diversity will be maintained. So, this is the way actually we ensure the population diversity. Now, we have seen that we are able to maintain the selection pressure as well as the population diversity. The method I have already discussed. Now, once we are able to maintain a balance between selection pressure and population diversity, now we are in a position. We are in a position to improve the solution further with the help of the operators like crossover and mutation. Now, after this reproduction scheme is implemented, now we go for the crossover and the mutation, and that completes actually one iteration or one generation of the GA. Now, this process will go on and go on through a large number of iteration, and ultimately we will be getting a Pareto optimal front of solutions. Now, before I end here, so let me solve one numerical example just to show you the working principle of this particular the sharing function. How does it work? How to calculate this particular the niche count value and how to find out the shared fitness values. Now, let me just try to concentrate on this small numerical example. Now, the same problem I am just going to discuss. I will have to minimize the two objective functions f1 and f2, and supposing that this is actually the rank 1 front. So, this is the rank 1 front, and let me assume that there are lying only 5 solutions on this particular the rank 1 front, say solution 1, 2, 3, 4 and 5, and supposing that these are the coordinates of these particular the 5 solution. That means, corresponding to solution 4, now the value of f1 is 4 and value of f2 is 2, and this is denoted by 4, 2. Similarly, I can find out the coordinate of all such points, and a particular the coordinate of a particular point indicates how much is f1 and how much is f2. And supposing that we have got only the 5 points here. Now, out of these 5 points, point 1 and point 5 are too far from the other points like say 2, 3 and 4, and let us see how to implement the concept of this particular the shared fitness, how to calculate that. Now, to calculate the niche count for this particular point 1. So, what I do is we try to find out the Euclidean distance between 1 and 2, and that is nothing but square root 2 minus 1 square plus 4 minus 8 square, that is nothing but square root 17, that is 4.12. Similarly, we can find out the distance between point 1 and 3, that is d 1 3, and exactly in the same way I can find out the Euclidean distance 5.38. Next is we try to find out the Euclidean distance between 1 and 4, and following the same principle I will be getting 6.71. Next is the Euclidean distance between 1 and 5, and that is nothing but this, and I will be getting 9.90. So, these are all Euclidean distance values calculated with respect to the point 1. Now, actually what we do is we will have to set some fixed value for this particular sigma CR, and let me assume that sigma CR is equal to 6.00. Now, if this is the situation, then now let us see how to find out the sharing function. The sharing function D12, that is the sharing function value between 1 and 2 is nothing but 1 minus 0 minus 4.12 divided by sigma CR, that is 6.00 square, because here the Dij is 4.12 and that is less than the sigma CR, that is 6.10, and that is why. So, we will have to use this particular expression to calculate the sharing between 1 and 2, and this will become equal to 0.53. Similarly, the sharing between 1 and 3, that is SH D13 is nothing but 1.0 minus 5.38 divided by 6.00 square, and here once again the Euclidean distance between 1 and 3 is less than 6.00. So, we will have to use this particular expression, and this will become equal to 0.19. Next is the sharing between the 1 and 4, the distance between 1 and 4, that is D14 is found to be more than 6.00. So, the sharing between 1 and 4 will become equal to 0.0. Similarly, the sharing between 1 and 5 will be 0.0, as the Euclidean distance between 1 and 5 is more than 6.00. Now, if this is the situation, now very easily I can find out what should be the niche count. So, the niche count for point 1 is nothing but 0.53 plus 0.19 plus 0.0 plus 0.0. So, this will become 0.72. So, for the niche count for this particular point 1 is nothing but 0.72. Now, next we try to find out the niche count for the second point, that means this particular point. So, we try to find out the Euclidean distance between 2 and 1. So, this is the distance between 2 and 1, the Euclidean distance between 2 and 3. So, this is the distance between 2 and 3. Next is 2 and 4. So, this is 2 and 4 2.83, then 2 and 5, and this is becoming equal to 6.71. Now, if I compare the Euclidean distance values with the sigma CR is assumed to be equal to 6.00. So, for this particular point the Euclidean distance is more than your sigma CR. So, its contribution towards the sharing function value will be equal to 0.0. Now, if I follow the same principle to calculate the sharing function value, the sharing between D21 is nothing but 1.0 minus 4.12 divided by 6.00 square, that is 0.53. Next is the sharing between D23 is nothing but 0.94. The sharing between D24 is nothing but 0.77, and the sharing between D25 is equals to 0.0. Now, I can find out the niche count for point 2, that is nothing but 0.53 plus 0.94 plus 0.77 plus 0.0. So, this will become equal to 2.24. So, this is the niche count for the point 2. Similarly, I can find out the niche count for this particular the point 3. So, I can find out all the distance values, like D31 is 5.38, D32 is 1.41, D34 1.41, D35 5.38, and very easily I can find out the niche count value. So, the sharing function value I can calculate between 3 and 1 is 0.91, between 3 and 4 it is 0.94, the sharing between 3 and 2 is 0.94, the sharing between 3 and 5 is 0.19, and now I can calculate the niche count for point 3, and if you just add them all such values, you will be getting 2.26. So, this is the niche count value for 0.3. Now, I see how to find out the niche count value for 0.4. So, the distance between 4 and 1, that means I am trying to find out the niche count for 0.4. So, we consider D 41 6.71, D 42 2.83, D 43 is 1.41, D 45 is 4.12. And here we can see that only this D 41 is more than 6.00. So, its contribution towards the sharing function value calculation will be 0, and others will have some non-zero value. And if I calculate, so I will be getting the niche count, the sharing function values are like this, and the niche count for 0.4 is 2.24. Now, let us see how to find out the niche count for the fifth point. So, this is the fifth point. So, once again we determine the Euclidean distance between 5 and 1, that is 9.90, between 5 and 2 6.71, between 5 and 3 5.38, between 5 and 4 4.12. And here if I see the Euclidean distance between 5 1 and 5 2 are more than 6.0. So, their contributions towards the sharing function value will be 0, and others will have some non-zero value. Now, if this is the situation, so very easily I can find out how much is the sharing function value for the different between 5 1, 5 2, 5 3 and 5 4, and if we just add them up, we will be getting the niche count for 0.5, and this is becoming equal to 0.72. Now, we have calculated the niche count value for all the 5 points which are lying on the rank 1 front. Now, let us assume that the initial fitness for all 5 solutions is equal to 100. Now, if this is the situation, now I can find out the shared fitness of 0.1, that is nothing but 100 divided by 0.72 is the niche count, and this will become equal to 138.89. Similarly, the shared fitness value of 0.2 is 100 divided by 2.24 is 44.64. The shared fitness of the 0.3 is 100 divided by 2.26 is 44.25, and similarly I can find out the shared fitness value for the other points, like that is for the fourth point this will become 44.64, and the shared fitness of the fifth point is 100 divided by 0.72 is 138.89. Now, if I compare the shared fitness values, for the fifth point and for the first point is somewhat higher compared to that of the other points. Now, if I do the proportionate selection based on the shared fitness, there is a possibility that I will be getting more number of copies of 0.1 and 0.5 in the mating pool. And if I get more copies of this 0.1 and 0.5, there is a possibility that this particular end information of this the Pareto front, that is 1 and 5 will not be lost from the population, and this particular the diversity or the spread of this particular front will be maintained, and there is a possibility the GA is going to find out a very wide Pareto optimal front of solution. Now, this is the way actually this concept of sharing works, that means how to ensure actually this particular the diversity in the population of this particular the G. And once we have done this particular reproduction scheme, we got the mating pool, and now we will go for the crossover and mutation that completes one cycle of the GA, and you will be getting the better and better solution, and GA will be able to find out what should be the global Pareto optimal front of solution. Now, this NSGA could achieve some success and popularity but it has got a few drawbacks. Now, let us try to mention those particular the demerits. The demerits are such, like here the performance depends on this particular the sigma share value. Now, it is user defined. Now, how to set this particular the sigma share value, whether it is 6.00 or 7.00, that depends on the problem, and the user will have to define this particular the numerical value, and the quality of the solution will be controlled by this particular the sigma share. So, determining a proper value for this sigma share is a difficult task. The next is your the computational complexity. Now, this particular algorithm, that NSGA, is computationally complex, and the computational complexity is in the order of m n cube. Her m is nothing but the number of objectives, say it is either 2 or 3, and capital N is nothing but the population size. So, this particular algorithm is actually the computationally the slower, and its computational complexity is more. And moreover, in this NSGA, the concept of elitism was not used. Now, I have already discussed the concept of elitism, like if I get a good solution, I will have a direct copy of this particular good solution in the next population, and that means the already found good solution we do not want to lose. And as I told that this is almost similar to the fixed deposit, we do not want to touch, and we want to keep a copy of this particular good solution in the population. That is the concept of elitism, and this concept of elitism is actually not used in this particular the NSGA. These are all drawbacks of this particular NSGA. Now, how to overcome this particular the demerits of NSGA, that I am going to discuss. Thank you.